Today, I want to talk about recent joint work with Janine Heuer, Helen Naumann, and Timo de Wolf. And since the audience is rather diverse, I thought to spend the first couple of slides really just setting some basic context. So the underlying problem I'll focus on today is an unconstrained Zignomial optimization problem. So the functions we are considering here in this talk are Zignomials, sparse Zignomials. So what are these guys? These are functions supported on a real set A and look like this. So they are weighted linear combinations of exponentials of linear functions. The coefficients are real and also the support is real. So you can also think of Zignomials as a generalization of polynomials over the positive orthant. And the space of Zignomials I will denote with R to the A. And in particular, we are interested in sparse Zignomials. That means we only consider Zignomials with a few terms. And then we want to find the minimum of such a Zignomial globally. And clearly, this is a non-convex optimization problems having lots of applications like in chemical engineering, aircraft design, communications, etc. But since it's a non-convex optimization problem, this is hard to deal with. So we would like to have some good methods to solve those. And the first idea is to maybe use some algebra in order to learn something from this problem. And this brings us to the connection of non-negativity. Namely, we can equivalently to minimizing these functions, we can look at the problem of finding the smallest real number gamma, such that f plus gamma is non-negative for every x in Rn. So in this case, minus gamma would be a lower bound for our Zignomial f. So this means if we look at this problem from an algebraic perspective, what I really want to do is I want to decide non-negativity of a Zignomial over Rn. And of course, this is a key challenge in real algebraic geometry dating back to the 19th centuries of questions from David Hilbert and co. But just switching to the algebraic point of view doesn't help here because, of course, this problem now is decidable, but in general, it's NP hard. And therefore, one is interested in finding sufficient conditions to certify non-negativity, but which are easier to check. And these conditions are called certificates of non-negativity, because if we would have such a non-negativity certificate, I could relax this hard non-negativity condition to something I can actually check. And clearly, specifically in the polynomial setting, we have this old star certificate of non-negativity, namely sums of squares. Because clearly, if I can write a polynomial as a sums of squares, I can read off from this representation that this polynomial is non-negative. But it is even better than that, because if you give me a polynomial, I can decide if it is a sums of squares, and I can even find such sums of squares decomposition via semi-definite programming. But there is one drawback, as already mentioned in the talk from Didier yesterday. These semi-definite programs quickly get very large in size with growing numbers of variables. So in recent years, there have been lots of interest in finding alternative certificates and also alternative certificates adapted to this sparse setting. So to say, certificates which prevent sparsity of my underlying support set. And there are these two certificates, namely SONC certificates. These are originally invented for polynomials by Ilman de Wolf in 2016. And then a bit later by Chandrasekaran and Shaw under the name Sums of AMGM Exponentials, so SAGE. And to take really this Zignomial perspective originated by Chandrasekaran and Shaw. And here the underlying idea is to take the AMGM inequality to test function non-negativity. And these certificates can be detected in general via relative entropy programming, and in specific cases via geometric programming. And it doesn't really matter here for the sake of the talk what that is. It's just important that both of these problems are convex optimization problems. Okay, so the key idea, as the title already suggests, is that we want to relax now a global Zignomial optimization problem by optimizing over the dual SONC cone, building on two key observations. Namely, if we consider the dual SONC cone as a set of Zignomial functions, then this dual SONC cone is really contained in the primal one. So it also gives us a certificate of non-negativity. And then I can certify containment in this dual SONC cone, and also I can optimize over it by linear programming. And let me shortly outline the talk. So first I'll introduce SONCs properly and also what the dual SONC cone is. And after that, I will discuss this containment I just mentioned. And I also will present the linear program. And to conclude, I'll show you some numerical experiments. Okay, so in order to introduce sums of non-negative circuits, I have to start with explaining what a circuit function is. So let's fix a sparse support set A and recall that we consider these Zignomials. Since the support set is fixed, we can identify a Zignomial with its coefficient. Yeah, so we have this canonical isomorphism. So we view both Zignomials and coefficients as functions or elements in R to the A. Then we call a function or a Zignomial a circuit function if these three conditions are met. Namely, first, the support set of the Zignomial, so which is just A, is a circle. This is a minimally affine dependent set. Then second, the convex hull of A, which is the Newton polytope of my Zignomial, this has to be a simplex. That means that all but one element of my support is an extreme element of this Newton polytope. And the third condition here is just a necessary condition for any Zignomial to be non-negative, namely that the coefficient corresponding to such a vertex of the Newton polytope has to be strictly positive. So from this condition, it follows that there has to be one element in my support, let's say beta, which lies in the strict interior of this simplex. So you have this picture here. And that means I can write this beta uniquely as a convex combination of the vertices alpha and these lambda here are the so-called barycentric coordinates relative to the vertices. And then I can decompose now my support into a part containing these extremal elements, so to say the vertices of this convex hull and this one additional interior point beta. And then I can write the circuit function accordingly. And in particular, note here really that since these C alpha are strictly positive, the C beta, so the coefficient corresponding to this interior point, is the only coefficient which could be negative. So to say, this coefficient will decide about over non-negativity of this function. And how do we test now non-negativity of these guys? This is done via the so-called circuit number. Namely, we define the circuit number as this product. So here in the numerator are the coefficients corresponding to the vertices of the circuit function. And in the denominator and the exponents are the barycentric coordinates. Therefore, this number can be derived by the initial circuit polynomial immediately. And the crucial fact now is that non-negativity of the circuit functions can be checked easily via this number, namely only via this condition, that is the coefficient corresponding to this interior point is lower bounded by the negative of the circuit number. And by easily here, I really mean we only have to solve a system of linear equations. So now we know how to easily test non-negativity of these circuit functions. And now as for sums of squares, taking sums of these non-negative circuit function abbreviated as SONC, this gives us a certificate of non-negativity. And these functions also form a closed convex form, a cone clearly contained in the cone of non-negative functions. And before continuing, let me show you how this works in action. So consider this Zignomial here. So this is in fact a circuit function, namely we have this set of extremal elements as 0, 0 here, 2, 4, and 4, 2. So this is our Newton polytope. And inside of this lives this element beta, which is 2, 2. And now we want to decide for which coefficients C beta is this Zignomial non-negative globally. And I told you we can use this circuit number for that. So let's compute the circuit number for this function. So first we have to consider all the coefficients corresponding to the vertices, which are all 1. And then we have to compute the barycentric coordinates. We find out that they're all 1/3 in this case. And now we have to just plug in and compute. And we see that the circuit number in this case is 3. And hence we can conclude that F is non-negative if and only if C beta is at least -3. And if you look a little bit more closely, you can see if we really take C beta to be -3, then this Zignomial can be thought of as, so to say, the Zignomialized version of the Motzkin polynomial. All right, so now we go on and take or follow a common tractable approach in optimization, namely to use further knowledge on a given function. So for a given fixed Zignomial we want to minimize, we clearly have additional informations on the signs of the coefficient of this function. So we can decompose the support set into 2 disjoint sets, where A plus collects every exponent, so every support for such that the coefficients are non-negative. And I minus, I collect every support point corresponding to the remaining coefficients which are negative. And clearly these are 2 disjoint sets because, I mean, obviously my coefficient can only be non-negative or not, right? And then I can decompose, so to say, every Zignomial I consider following this sign pattern. So here, this first term has coefficients which are non-negative. Here are the negative ones. And again, this is the set A plus, and the betas are contained in the set A minus. And accordingly, I now define the so-called signed SONC cone, which I give this symbol here as plus sub A plus A minus, as the cone of all sums of non-negative circuit functions restricted to this given sign pattern. And additionally, we add non-negative exponential monomials supported on A plus. So these are expressions supported on a single element. So these guys here. So now we know, so to say, the primal SONC cone in this game. Let's talk about the dual. So notation-wise, now everything with a check over the ladder corresponds or indicates duality. And first, we consider clearly the natural duality pairing between a zignomial F with coefficient vector C and an element in the dual. This is given as usual. And here, as for the primal case, we identify this dual element with its coefficient vector. And again, we consider this coefficient vector being in R to the A. Then, just by definition, the dual signed SONC cone is given as follows. So here again, this check now. These are these elements in R to the A for which this natural duality pairing is non-negative for every function living in the primal SONC cone. Yeah? So this is just the definition of a dual cone. In what follows, I often drop this signed and just refer to this cone as a dual SONC cone. But what we do now is we show specific representations of this cone. Namely, we show two different representation of this dual SONC cone. Namely, one is, so to say, lifting free, and one contains linear auxiliary variables. So to say, one is a lifted version of this SONC cone, and we add as many auxiliary variables as we have interior points in our convex hull of the function. And we really, in what follows, need both representations of this dual SONC cone. Namely, the first one we use to show this containment of the primal and the dual, and we use the second one for our optimization purposes. Okay, so as indicated in the beginning, we want to now somehow view the dual SONC cone as a cone living in the zignomial space. So what we hence now do is we identify this dual cone with the cone of all zignomials of this form, where we just say we pick these zignomials where the coefficients are in the dual, and these f beta then are strictly negative. So again, since we now want to somehow identify this dual cone with cone of zignomials, we just say, okay, we take these zignomials now as living in the dual SONC cone where the coefficients lie in this dual signed SONC cone. And moreover, we have to here really scale the vectors from this dual SONC cone, otherwise it does not work. So we can in particular say not every element in this dual SONC cone induces really a function in the dual. And this so defined cone of zignomials, which are somehow dual, we denote with f s hat plus a minus to somehow indicate this is the function dual SONC cone. Okay, with that now we can really follow our path. Namely, first we want to show that this dual SONC cone is contained in the primal cone, and as said, we use the first representation of this dual SONC cone, namely the lifting free version for that. And this more or less directly yields that this dual SONC cone, if we really look at it like just defined as functions having coefficients in this dual cone, this so constructed dual cone is really contained in the primal one. And what does that mean? That means in particular that every function in this dual cone is non-negative, because clearly this SONC cone is contained in the non-negativity cone, right? And that means every function here in this cone also gives us a non-negative certificate. Probably not as good as using the primal one, since the reverse containment does not hold, but it gives us a non-negativity certificate we can use for optimization purposes. So then another thing we have to address now, how do we check membership now in this function dual cone? And recall, we consider these Zignomials as living in this cone. And we want to know how we could test if such a Zignomial really lives in this dual cone. And then a specific linear feasibility program does this. Namely, it just checks this condition. And this program, you see, is in as many variables tau as we have interior points. So for every interior point, we have to check if this inequality holds. And if it does, then we know that this Zignomial is contained in this function dual cone. And the way we prove that, or rather the proof idea, is to use this second representation of the dual SONC cone, namely using this lifted version, because this tau, these variables here of this feasibility program are exactly these linear auxiliary variables. Maybe one word, because you might say, oh, this is maybe not linear, right? Because we have here the logarithm, but since we fix the Zignomial, clearly the coefficients are fixed. So this expression here is really then just linear in tau, which leads to a linear program. Okay, so now we know this containment and how to check membership in this cone. So let me quickly remind you, if that was a little bit too technically, what we wanted to do. So we have this global Zignomial optimization problem, which we equivalently formulated as finding the largest or the lowest gamma, such that f plus gamma is non-negative. So we wanted to find a lower bound for this question. And now we have a new certificate of non-negativity at hand. So usually we would now relax this non-negativity condition by a SONC condition. And now we don't do it with the primal SONC cone, we do it with this new established dual SONC cone. So we now relax this hard condition to a containment condition in the dual SONC cone. So we define here this number gamma hat star as the smallest gamma, such that f plus gamma really lies in this dual SONC cone. And maybe one thing I have to note here, namely this 0. So the 0 is not necessarily contained in my support. And in our work, we really discussed this general case and how to somehow choose a way how we can know where it is contained in either A plus or in A minus. But to really make things easier here, we assume that 0 is in the vertices of the convex hull. And this means that 0 is contained in the support, and it also is, or even more, it is contained in A plus. And this means that our Zignomial under consideration has a constant positive term. Okay, with this consideration, this is the linear program. And don't look at it too closely. I just want to point out a few things here. So again, we consider these Zignomials here of this form following this sign pattern. What I only did here is I separated the constant term. Then this is the linear program we solve. This linear program has the cardinality of A minus, so as many elements of the interior point plus one variable. So again, we have this variable coming from this containment feasibility program tau, and we also have this variable c. And then the constraints here just test, so to say, the containment. So you can see that these are, again, these inequality conditions. And these inequality conditions I have to test again for every interior point and every vertex. And I only have here one maybe extra condition coming from really the constant term. And why do we have now to substitute C? So usually we would here minimize this function, but clearly this would then not be linear anymore. So what we do is we substitute the C in this program to linearize this program really, and in the end, clearly to find the optimal value, we have to resubstitute, which happens here for this minus gamma hat star, where we really resubstitute with the exponential functions here, this variable C. And maybe already one word to the numerics here, namely, I want to stress the fact that, in fact, we solve here a lot of linear programs, not only one linear program, since we have to decide this year for every interior point beta and each vertex alpha. So if we have maybe, say, many interior points, it could be the case that it's slower than we maybe think. But clearly, since we have linear programs, it's numerically extremely stable. Okay, so this is the linear program. And I think now we come to the interesting part. So let's talk about some numerical examples. And we compare here different algorithms. Namely, we compute bounds via 4 different algorithms. So dual SONC indicates the bound I just introduced via relaxing our optimization problem with the dual SONC cone. Then we take SAGE into consideration. This provides us the optimal primal SONC bound, and this is based on relative entropy programming. Then we take the primal SONC into consideration. So this is the covering algorithm, which is, like I said, based on the primal SONC bound. So this algorithm, what it does, it computes the circuit decomposition of the ground set. And this is based on geometric programming. But it only provides a lower bound for the optimal SONC bound, because this circuit decomposition is sometimes not the optimal one. But it only relies on geometric programs and not relative entropy programs. That means it is experimentally has better run times than the more general relative entropy programming. And last but not least, we consider sums of squares. So the bound computed via solving semi-definite programs. And here already one word to that. So we really take the general sums of squares approach. So there are clearly also approaches out there which are better suitable for sparse functions. And this is really a work in progress, so to say, to compare this sparse sums of squares with this new approach, but just for, so to say, sake of completion, we added this normal sums of squares bound. And 2 notes before coming to examples, namely, first, it is possible that this bound SONC is worse than the bound dual SONC, which might be a little bit strange because, the dual SONC cone lies in the primal. How can then be the primal bound worse than the dual? This is because, as I mentioned, for the primal SONC bound, we have to compute a circuit decomposition of the ground set, and it just computes a circuit decomposition. So we might end up with a non-optimal one. So hence we can really have here that the SONC bound is not as good as the dual SONC bound. And on a related note, the new dual SONC bound can never be better than the bound given by SAGE, because as said, this bound SAGE, this provides really the optimal SONC bound. So with our dual SONC bound, or at least for quality, not runtime, for quality purposes, we can never be better than SAGE, provided both bounds can be computed successfully. Okay, so first example discusses a polynomial and two variables of degree 8 with 3 inner terms. And this is somehow an example what we, so to say, expect. So the best bound here is provided by the SONC, by the SAGE algorithm, but both the SONC and the dual SONC approach have better runtimes, where again the SONC approach has slightly higher runtime than the dual SONC. And again, this is due to the fact that we may have to solve linear programs or many linear programs. And the second example is a polynomial in 10 variables of degree 30. And the convex hull of A is a standard simplex. Here we see that both SAGE and SOS fail to compute a bound because it's really just too large. And interestingly, the bound provided by our dual SONC approach is better than the primal one provided by this covering algorithm. And this is, of course, because of the reason I mentioned, due to the possibility that this primal SONC bounds are possibly not exact. But this nicely shows that taking this route is really a valid and interesting route and should be also further exploited. Okay, I think I am ready to wrap up. So your take-home message is that these results I presented provide really an effective algorithm for optimizing over the dual SONC code. In general, clearly this new approach provides worse results than the SOS bound and the primal SONC and SAGE approach. But since we only rely here on linear programs, it's computationally much more stable and also has promising runtimes. And what also is interesting, it gives a result whenever a solution in the dual cone exists. And clearly, this dual SONC cone is independent of this existing primal SONC and SAGE algorithm. So it's always important to add new somehow algorithm to our toolbox that we can try for, I don't know, Zignomials which are not suitable for these other algorithms, new algorithms we can work and tackle with. With that, thank you for your attention, and here some references, and the results from this paper, from this talk, are to find in this paper here.
Great, thank you, Mareike, for a very nice talk. Questions or comments?
I would like to ask a question. So this is clarifying something I was probably confused. So I thought you said something that like dual SONC gives usually better solution than primal SONC because like there is not a unique circuit, but then in example 1, it seemed like the primal SONC solution was better, but I think I misunderstood something.
Exactly, so it's exactly the opposite, because so the dual SONC cone lies in the primal one, and hence from this perspective, the primal SONC cone clearly gives better results.
I see, yes.
Yeah. And that's why here we also see that it gives better results.
Can you then maybe say again what you said about this? Because there is like the circuit representation. So was that something for the dual SONC that influenced?
Exactly.
Okay.
So it is now the following: how the primal SONC approach is implemented is that if you have a support set, then this algorithm decomposes this ground set in circuits. And how this works is not in an optimal way, so it just finds a circuit decomposition. So it, so to say, triangulates the ground sets in any way. And if it did find some, then it stops. So it does not optimize over this circuit decomposition. So this decomposition which is found by this algorithm is maybe not optimal. So the bound which is then in the end computed with this algorithm is maybe not the optimal. And if it's not optimal, then it may happen that the dual SONC approach could be better. But if it would compute the best decomposition, then clearly we cannot be better. And this best decomposition, so to say, is computed by Sage, but this is not really true because they are not relying on circuits, but yeah.
Thank you. Thank you for the excellent talk. It was very interesting.
Thank you.
Any other questions or comments? Good. So we'll thank Mareike again, and I guess we'll take a break now for 40 minutes and we'll resume at 3:20